Okay, welcome everybody to the next installment of our reading group. Today we're really excited to welcome Zheng Wu and Aryaman Arora. So Zheng Wu is a second-year PhD student at Stanford University, co-advised by Christopher Manning and Chris Potts. He received his master's from a symbolic systems program at Stanford University. Before that, he received his bachelor's degree in aerospace engineering and worked in cloud computing. Aryaman is a first-year PhD student at Stanford NLP, advised by Dan Jurafsky and Christopher Potts as well. Currently rotating with Noah Goodman, and his research is focused on interpretability of neural language models. So today they're going to be going through ReFT, representation fine-tuning for large language models. Instead of adjusting model weights during fine-tuning, ReFT focuses on modifying the model's internal representations to quickly fine-tune using up to 50 times less parameters than traditional PeFT models. So really excited to welcome you both today. Yeah, the floor is yours.
Okay, I'll share my screen.
Sure.
Can you guys see my screen?
Yeah.
Can you guys see the full screen?
Yeah.
Okay, great, yes. Yeah, thank you so much for inviting us, and thank you so much for the introductions. Today we'll give a talk about our recent paper called ReFT, stands for Representation Fine-Tuning for Language Models. And this is a joint work with a large team. So I'm Zheng, Aryaman is here, and we have Peter, Atticus, and this project is advised by Dan, Chris Manning, and Chris Potts. So just to give a headline of what ReFT is. So ReFT, it's a new approach for parameter efficient fine-tuning. We think it's not just a variant of LoRa or adapters. Hopefully we can convince you that by the end of today's talk. And ReFT, it's directly built on representation editing work from interpretability. Aryaman will cover some of those interpretability work in the middle of the talk. And overall, ReFT match or exceeds the performance of LoRa with much fewer trainable parameters. This will be the outline of today's talk. I'll first go through the background, introduce PeFT, and then move from PeFT to ReFT. Then I'll cover the main results that we put in the paper. We'll end the talk with some of the ongoing exploration of ReFT and some bit of future work discussions, and open up to Q&As. Now for the background. So this is a simplified overview of current parameter efficient fine-tuning method. So all of those methods, instead of tuning the full model weights, it tune a new model, a thin model components, or some added in embeddings. So if we go through them one by one for prefix tuning, so instead of tuning the model weights, it keep the representation frozen, but it adds in those trainable embedding matrix in one layer or multiple layers, and only tune those embedding matrix to meet the downstream task performance. And by doing this way, the trainable parameter count is really small. But in practice, it's prefix tuning is actually usually underperforming compared to adapter and LoRa. Now for adapters, it's different from prefix tuning. Instead of tuning those added in trainable embedding matrix, it added in a new model components, which called adapter layers. And this is one way of adding in adapter layers, which is a serial way. So basically adding this thin trainable adapter layers in the middle of the model computation, and by frozen all the model weights, just train the adapter layers and try to meet the downstream task objectives. And currently, I think the most popular way of doing PeFT or parameter efficient fine-tuning is LoRa. So LoRa is slightly different from the previous two methods. So it actually sort of tune the model weights, but instead of tuning the original model weights, it learns a weight depth that can be added into the original weights. And specifically, to learn that weight depth, if we learn the shape as in the original weights, it will be just like the parameter count will be just like for fine tuning. So instead of doing that, it actually approximates the weight depth by two low rank matrix. Here, show on the right hand side, we have A and B. Those two are low rank matrix. And then by doing matrix multiplication, it can actually approximate a weight depth that's in the shape of original weights. And eventually, this weight diff can be merged in the original weights to kind of propose a new set of weights that it's task dependent. And overall, one benefits of LoRa, I think one special benefits of LoRa, comparing to previous methods, is that there's no inference cost because we can merge the weight diff into the original weights. That at model serving time, you're still doing the original inference, unlike adapters. So adapter adding this additional computations. Okay. So to summary, those soda PeFT methods like LoRa, they usually target model weights instead of the representations. But we can actually unroll the LoRa kind of model component view into a representation view as well. So on the right-hand side, we have a very simple diagram showing that we apply LoRa to some, model components, which is depicted as a gray box here. So this is a model component view, right? So usually for language model, the input sequence contains tokens. So we can actually unroll this model component view to a representation view. Where essentially by applying LoRa to a certain model components, we're essentially editing the representation across the whole sequence. So across, for all the tokens, we're applying this LoRa edits. And to summary, by updating the model weights like LoRa, PeFT essentially change representation across all the time step. So with that, I will introduce ReFT. Right. So just to recap the previous slides, right? So PeFT update the model weights, thus change the representation across all the time step. So we essentially ask the question, whether these two parts are necessary, right? What if instead of updating the model weights, what if we just learn a set of interventions that change the representation across a few time steps? And actually, we want to push the time step as small as possible. So to again show how we actually do the intervention. Comparing to LoRa is that instead of modifying the representation across all the time step, what if we just learn, for instance, like one intervention, then modify this token I+2? What if by learning that intervention, can we actually achieve the downstream task objectives? Right. So that's the representation view of ReFT. And one major question is how we actually do the interventions, right? So the first kind of characteristic of the intervention that we do, it's where we actually place the intervention in. Again, if we go back to the LoRa view, the representation view, and this is just showing one transformer block inside the model and for a single time step. So if we apply LoRa to this attention output matrix, which people usually apply to, besides those QK matrix and then MLP matrix. If we apply LoRa, then essentially you can think of LoRa. It's again coupled with this attention output matrix, but again it's sort of acting as an intervention that modify this local representation, which is coupled with this attention output weight matrix. Since LoRa it's deriving this weight diff. So what we do is slightly different. Instead of targeting a specific weight matrix or coupled with them, we actually design intervention that's not coupled with any model weights. It can though, but it's like a thin adapter that applies to any computation stream within the transformer block. So specifically in our case, we apply to the main residual stream. We will reiterate again on this, but as you can see, in a high level, intervention can be applied to any computation node that doesn't contain any model weights. So for instance, residual streams, or you can place the intervention here, which is the self-attention block output, which doesn't contain any weights. So that's the intervention. So where we actually apply the intervention, there are other design choices for the interventions. For instance, how we actually parameterize the intervention. So we name it as a phi function. So how you actually design the phi function. And after we define the interventions, we also need to decide where we actually apply the interventions on. So which layer and what positions. So in summary, ReFT, it's nothing but just a list of intervention that it's parameterized by three parameters. One is the phi function, which is the intervention function that you want to design. We present two intervention functions in the paper, and then where you want to apply the intervention. Currently, we approximate that with two variables, which is the position, essentially the token position indices, and then the layers. So which layer you're placing these interventions on. So this is another simplified picture depicting how we actually apply the interventions. So you can apply this green phi function across multiple positions. So you can think of like these interventions applied to token I and I+2 are showing the weights. And you can have another intervention that's applied to token I+1, which is a different phi functions. And then I will hand over to Aryaman to talk more about how we actually parameterize phi function in the paper.
Yeah, so there's a lot of possible ways that you could go about creating an intervention function. Some previous works have done interventions on residual streams, so that's like representation engineering and stuff, and they had some methods for doing that. We were curious about like a function with learnable parameters instead of some fixed edit. So what we were inspired by is existing work in interpretability. So in interpretability, we had this tool called distributed interchange intervention. And essentially what this does is, given some representation, it will take a linear subspace of that representation and modify only that using a counterfactual representation without changing anything outside of that subspace. So the reason for using this tool is like, if you have some information and you want to localize it in a representation, so this could be like linguistic information, or basically anything that you want to study that you think is a feature in the transformer. Distributed interchange intervention allows you to find that subspace and like perform a very surgical edit to only edit that, and while leaving the rest of the information intact. And the neat thing is the subspace that you edit on, that can be found with gradient descent. So here's the equation for distributed interchange intervention. I'll just walk you through it. So one thing you got to notice here is that this requires two representations. You need your base representation, which is what you're trying to edit, and then a source representation, which is a counterfactual. So like if you're studying like linguistic number, like singular versus plural, maybe the base is a singular thing and the source is a plural thing, and you want the model to believe it's a plural thing. And then the subspace you're going to perform the edit in is R. So R is a projection matrix with orthonormal rows. And this is like, it projects from the full rank down to the low rank. So let me do the next slide. Yeah, so the end result is like, you take the difference of the representations in that subspace, and then you up project that back up, and you get an edit vector that's in the subspace spanned by the columns of R. And then you just add this edit vector to the original representation. So you can think about other work in like concept erasure or like representation engineering as doing sort of similar things, but with different intervention functions. So for our purposes, like we want to adapt this to
Could you very quickly actually, sorry, just because I didn't follow all of that. Basically, just on a high level, because the bit about gradient descent, you're basically saying that. So can you go back a couple of slides actually? So you mentioned the slide before this one as well, actually. You just mentioned about gradient descent being able to be used to find an optimal subspace or something like this. Maybe you're going to explain this, but what's the objective function in that gradient descent algorithm? Like, what are you trying to optimize the subspace representation to be? Like most expressive or something?
Right. So when you use distributed interchange intervention for interpretability stuff, what you're optimizing is the model's behavior. So the output behavior specifically.
Okay, sorry, I understand. Sorry. So you just okay. So this is just like the architecture. This is like the I don't know. You have like a projection. You have this matrix, and these are the learnable parameters of this transformation matrix are kind of where the gradient descent is, and you find this optimal subspace that does well on the final task. Okay.
Yes. The subspace is R is the learnable parameter here, and all you're doing is like you have some base. You're gonna like edit some subspace of that representation while leaving everything else the same using the counterfactual S that you have. So like if you want to edit like a linguistic feature, you would edit.
How are these initialized? Are they initialized so that there's no intervention? So that's like zero impact on the intermediate. Like, is it initialized so that this does nothing?
So actually, no. We just sample like random vectors. Like it seems to work fine. You don't have to initialize with zero like you do with LoRa. So
interesting. So even though the initial state of the network is actually not producing perfect outputs because you've initialized it randomly and like you're therefore perturbing it, it's still able to train and get a decent performance in the end.
Yes, yeah. Because this is like a ridiculously small number of parameters usually. So because you're projecting from representation space down to the low rank, so it ends up being like in Llama 7b, representation space is 4096 dimensionality, and the low rank might be like 4 or 2 or 1 or something. So really small. So it's a very small number of parameters, like on the order of thousands.
Okay, got it. Okay, sorry, I just didn't fully follow that, but it makes sense.
No, that was a very good question. Yeah, I think this part is the most math in the talk, and it's good to make sure people understand what's going on.
Awesome.
Cool. Yeah. So that was for interpretability. We have this equation. So one problem with this setup is you need a counterfactual. Like if you want to modify some model behavior, you need like this is what you're trying to edit, and this is what you're using to perform that edit. But like for real world fine tuning purposes, we don't always have like paired data like that. We want to be able to learn like how the model does the steering. So we modified this equation by replacing that source with a learned source, which is just a projection of the base representation. And so all we're doing is like we learn some subspace. In that subspace, the edit we're performing is a learned transformation of the original representation. So this is the final equation for low ReFT, which is we're calling low rank.
Actually, again, these might be silly questions, but this is an area I'm not super familiar with. But so obviously right now you're not like applying this to a matrix. So with LoRa, obviously you're kind of transforming the existing matrix. But you're saying here that it doesn't even need a matrix to hook onto. It can just be like the kind of the activation at the output or something, and then you apply a transformation to that activation, basically. So it's not like modifying a transformation matrix. It's like modifying the activation directly, basically.
Yes. So where would A tier is a representation? So
what would just to understand? So you have the base and the source. Sorry, could you just quickly describe again what the base and the source mean?
Yeah. So that was for interpretability. Like when we got rid of the source because we don't want paired data. But like let's say you're trying to study how does a model represent singular versus plural. You have some like example like the man goes and the transformer predicts a singular verb for when the man is subject, and then your counterfactual input is going to be like the men go because there's a plural thing. And what we're going to try to find in the model is there some subspace that totally like isolates the singular versus plural, and then we'll like copy and paste men into man, like some part of that representation in that subspace, and then we'll hope that the output behavior of the model changes to make it think it saw plural noun instead of singular one. Yeah.
Okay. I think that makes sense. I will let you keep going. I might have a few more questions.
Feel free to ask more questions. I think this is definitely the most confusing part of the talk because not everyone is like interpretability has been moving super fast, and there's a bunch of like
I'll admit that I'm not deep in the weeds on the latest interpretability research, but I understand that on a high level. But basically, okay, so the base and so just in that example you gave, sorry, so you gave an example of like a case where it's plural and a case where it's not plural, and the idea being that there's a way of kind of isolating in the representation like where that concept of plurality is contained and being able to like perturb it such that the model goes from thinking things are plural to thinking they're singular or something like this, basically. That makes sense. But just sorry, explicitly, so the base and the source, like what are they mathematically exactly? Is it those two examples? I didn't fully follow what you mean.
So they're aligned representations between the two examples. So this could be like layer 3 residual stream output, like something like that, where like just two representations that you're trying to.
Okay, got it. Yeah, representations of this kind of concept, basically. Okay.
Yeah. So like nth layer, it could be like the embedding input. It could be any like part of the model.
Yeah, and so in conventional, so let's say in conventional interpretability literature, that is kind of why you have this concept of base and a source, because it's kind of two different concepts. And this is the representations of these two kind of semantic concepts, basically. Is that correct?
Yes. So it's like
and you're kind of using this,
and
you're kind of Yeah. Okay, I got it. And you're kind of like using this as a starting point. You're kind of taking this equation from the interpretability literature and kind of then amending it to kind of in this kind of more low parameter, like optimization, like space. Okay, I'm following.
Yeah.
Okay. Yeah. Thanks.
Yeah. So just like in that thing, it was like, we want a subspace that isolates a feature. We got two examples that show that feature difference. For us, it's like you have some big data set. We think like we can find a subspace in the representation space that makes the model behave in a way that we want it to. Like, yeah. So yeah, this is the question. And I think we had one question in the chat. Why don't you use an R matrix with D times D dimension instead of duplicating the process of multiplying? So the whole point of this whole, like, we down project and then up project to like from a smaller dimension to a higher dimension. So it's just like LoRa, it's a way to save parameters and reduce the search space. Because instead of having one big matrix, we can like have two halves of a, you know, a down projection and an up projection. Yeah.
Awesome, thanks.
Yeah, so you know, this equation is pretty complicated and involved. So you might be wondering, like, is this equation necessary? Like, do we need this to be so complicated? So like we have orthogonalization enforced on R, and we have all these parameters. So obviously we agreed. So we tried a bunch of alterations to this equation, ablations, that involve simplifying things or getting rid of some parameters. So I'll talk about more of these later, like the results we got. But the most interesting one here is what we call DiREFT. So it's like it's basically the same equation as LoRa. There's just a down projection and up projection, and that gets added to the representation. So we're calling this like a positional LoRa, and it's a test of, does the benefit of our method come from like the specific equation for LoREFT, or is it just like applying stuff to individual positions is what's powerful? Yeah. So that covers the intervention function phi. So we have two other components of an intervention: the position P we want to apply it at, and the layer L that we want to apply it at. So naturally, like, how do we do this? This is a huge number of hyperparameters compared to other PeFT stuff, because they don't ever have to think about what positions to do the intervention on. So our belief is that you only need a few positions. Like if you look at that representation view, a LoRa is applied to every single position in the layer that it's being done on. So like, on the other hand, like, we can be more selective in which positions we want to intervene on. So let's consider like LoREFT applied to a single position.
But very quick question, like, given that LoRa's learned,
yeah,
if it's really irrelevant, so it doesn't have any impact on inference speed. So it's not like you're paying in compute for these adapters being applied to every layer of the network.
Yeah, well,
and I
only
guess
if you
it's
merge
really
in.
Okay, yeah, sure.
Yeah.
Okay, that's what you're saying. Yeah. But I guess like if it is not needed to be applied on a later layer, it would just like learn an identity. It could just learn like an identity function or something, I guess. So I guess in a way, LoRa could learn to like only apply itself to some small regions. Is that something you think LoRa typically does? It kind of only learns to focus its transformation on really important layers, or do you think it like needlessly kind of, I don't know, distorts all of the matrices more than it needs to?
Well, I think it has a bit of a tough job because it's applying the same function at every position.
Position, yes. I was thinking about the layers.
Position,
like,
layers. Yeah. I mean, per layer, yeah, sure, it can learn not to intervene, right? Because
but you're saying I got it. But your point is that you actually also only need it in
our point is positions. Yeah.
Okay, interesting. Well, that's true.
For us, it seems
supposed to be the same.
Yeah, you're doing the same function additionally at every position, and we think you can get away with like less positions.
It could also be better, I guess. Strictly speaking, if the perfect solution is to like change the structure a lot at these positions and not change it at all at these positions, if that solution is superior, then LoRa can't find that solution either, I guess. So
yeah, I think it would be much harder because it's forced to do the same thing.
It's forced to do the same, isn't it? Yeah.
So in some sense, this is learn differential.
Yeah, that makes sense. So this is much more expressive in the time dimension, basically, in terms of what the representation can look like.
Yeah. But then the downside is we got more choices to make from a human angle. Yeah. So we think like a few positions is enough, because when you perform an intervention at a representation, like anywhere in the model, everything in later layers and later positions gets affected, even if you don't change the weights, just because attention propagates that change downstream. And so naturally, like now we're thinking from an engineering point of view, how do we make this as simple as possible for the user while like still getting good performance and making it easy to hyperparameter tune? So our initial thought is, let's only intervene on the prompt, because for almost all tasks we have a prompt and then the model generates a response. And the neat thing is the prompt is always processed in one forward pass. So if we can just hook onto that forward pass, we just add a like initial upfront cost, and then like generation time, we're not adding any more costs. So that makes sense from an engineering perspective. Then the question becomes, inside the prompt tokens, which tokens do we want to intervene on? So our thought was, let's take a fixed length prefix and a fixed length suffix of the prompt and only perform our intervention there. So, we already talked about this can be done in one forward pass. Another good thing here is like you have some prompt. No matter how long or short the prompt is, we're only processing the same number of tokens. So our additional inference cost does not scale with the length of the input. So the overall result of this is like you can't merge it back in like LoRa, but like we can get pretty close to having very little inference cost. And of course, you can either tie the weights across all those positions like LoRa would do, but you can also untie them and learn a separate intervention at each position. Yeah, so overall, we apply LoRa to a fixed length prefix and suffix of the representations in the prompt. We know this will propagate downstream at decoding time because of attention. There's no additional inference burden during the decoding. But in that first forward pass, there's only a fixed cost and it doesn't scale with prompt length. Because once you process the prompt, all that stuff gets cached in the KV cache. Yeah, and like we mentioned before, these interventions, we apply them to the residual stream. So like for a transformer block, it takes some input and it produces an output representation that has some contextualized stuff that attention has done, and then the MLP is applied. So we apply our interventions to that output. Yeah, and so like for practical purposes, here's a list of all the ReFT hyperparameters. Yeah, so you can see a lot of these are the same as LoRa. What's different is like positional information, like what positions we want to apply at. So that is some additional search compared to LoRa, but overall it's not too bad. I think this is definitely the lowest we can bring it down to in terms of practicality. And now Zhen will talk a little bit about the results and show us some pretty figures.
Great. Yes.
Very, very quick question actually just on this. Sorry, I know I've got a lot, but in terms of those hyperparameters then, so they're things that you decide ahead of time. You don't try to do some kind of optimization algorithm based on the task to learn the layers or anything like this, because obviously you do the prefix and the suffix. So I understand that the time-based stuff, you just have a fixed amount on the beginning set and the end set. In terms of the, and you said it's applied to some like latent representation of all the prompt tokens. Is that like, I guess what depth of the prompt encoding is it applied to? Is it only applied once?
No, so you can, because we can do multiple interventions, right? And the weights don't have to be tied. So you can do all the layers, like, and then so what we found is doing all the layers is the best, but you can like shave off some layers and you'll get like diminishing performance, but like the parameter count will also go down.
Interesting. Yeah, it's interesting.
Yeah,
so
and it's a separate intervention for each layer, so they're separate parameters.
Yeah, that's interesting. I guess it really, well, obviously jumping ahead, but I guess it'd be really interesting to try to like learn those high parameters as well potentially at some point.
We totally agree. Yeah, like this was just so this is sort of like prefix tuning actually, where they also looked at adding tokens to prefix or suffix or an infix. But like I think what definitely is the best is like if we can optimize it automatically during training or something. And we're definitely thinking of ways to do that. Oh, and another thing is intervening ad decoding steps might help the model stay on track in like long form generation.
There's probably ways you could do it in a gradient based way. I guess like you could do it in just like a non-differential optimization search or something. But like if you applied like one to everything and you looked at the ones that start to get closer to the identity and then like pruned them away or something like this maybe. But
or you could do like gating, like people have been doing these days with like mixture of depths and stuff like that.
Very interesting. Anyway, sorry, I'll let you guys continue. Brilliant.
So I'll let Zhen explain.
Right. Yes. Yeah. Wait, can you still hear me?
Yeah.
Okay. Great. Yeah. So just on top of the hyperparameter search element, you can obviously also do the kind of Rome model editing pipeline where you first localize the knowledge and then you do the edit. So something similar can be applied here as well, where you do a search per task search of representations, do some ablation studies, and then apply intervention on top of that. But we didn't end up doing that in this draft. With that, I will go to the results. Again, just to reiterate, so with the most updated version on archive, we now have two parallel way of parameterize the phi function, which is low reft and die reft. Low reft, it's with additional constraints on the transformations. We have the rotation matrix, which only contains orthonormal rows. And then we have a free learn weight matrix plus a bias term. Die reft, it's much more like LoRa, which is parameterized by two low rank matrix W1, W2 with some bias term. Again, we see die reft is crucial because that gives us insights of whether applying LoRa-like transformation to the residual stream across a few time step actually make the difference, or it's a low ref formulation. So that will tell us what's the real gain on low ref is. Okay. So this is the overview of results. I will go through them in detail one by one, but overall we tested low ref and die ref or reft, two reft methods across 4 different benchmarks for different domains: common sense reasoning, arithmetic reasoning, instruction tuning, and classic natural language understanding or glue tasks on much smaller models. On the plots, we have parameter account on the x-axis and performance on the y-axis. As you can see, the real North Star here, it's definitely the upper left corner. And low ref and die ref, it's definitely moving towards that corner. I try to be more parameter efficient while keeping up with the performance. With that, I will dive into the benchmark one by one. So the first benchmark we look at is common sense reasoning. So it's the classic common sense reasoning benchmark, contains 9 or 8 data sets. Every data set is formulated as a multiple choice task. So this is one example for Winogrand. So we will say, please choose the correct answer, blah, 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 and give the Q questions and give the options for the model to choose. And also instruct the model what's the correct format is. And the response is just a single or multiple tokens. Right here we have option 1 probably tokenizing to 2 tokens, but overall this is like a short form generation, which is much more like a multi-token classification task, or even you can think of as a classification task. So if you think about the model in a model steering perspective, this is very easy to achieve because the output space is very limited. But on the other hand, this involves a very heavy parametric knowledge retrieval inside the model. So with that, let's look at the results. So with the updated draft, we compared against the PeFT methods. Specifically, we focus on LoRa and Dora. On Dora, it's one of the newest variants of LoRa, and it's probably one of the best LoRa variants out there. Just came out this year. And we benchmark on the common sense reasoning benchmark against LoRa and Dora for 4 different model type, but it's all belongs to the Llama family. So from Llama 1, 7B, 13B to Llama 2 and Llama 3. We have die ref and low reft, which is bolded. As you can see, it's pretty consistent that die ref and low reft outperform LoRa or even Dora. Again, this, not to mention, much less tunable parameter count. And as Aryaman and you guys talked about before, is that we actually did the hyperparameter tuning in a fair way or rigorous way, because the way we choose the hyperparameter for die ref and low ref, it's with a separate training set. Specifically, we use GSM-K training set. So we split off GSM-K training set for 300 examples and use that as our dev set to hyperparameter tune our die ref and low ref. And then we apply this, the end result of that hyperparameter tuning pipeline directly to retrain on common sense reasoning. So we ensure, this also test this is fair and also test out the generalization ability a little bit for die ref and low ref. As you can see, we with much fewer parameter count. And one nice thing about die ref and low ref or ref in general is that you can also see that this almost scales with the model quality as well. So from Llama 7B, there are some data sets that Dora does better, or Adapter does better for Llama 13B. But as we're moving towards Llama 3, you can see that die ref and low ref actually beats all of the beats LoRa and Dora across all of the benchmarks. So we see that this is a promising sign that ReFT also, or representation fine-tuning, also scale with the model quality. So this is especially a good sign since representation fine-tuning, it's actually editing the representation. If representation contains clean and much better semantics representations, then it may actually make it easy for ReFT to tune up.
Quick question. is this with it applied to every layer during the prompt encoding?
Yes.
Okay.
I believe so.
And how many? I'm sorry. What model is it applying it to actually? Oh yeah, I've got them. Yeah, all the llamas. Okay. And how many layers is that typically? Actually, I guess like for 7B or something. Like, how many layers is this like typically for these different size models?
32, I think.
Okay.
32 layers. Yes.
Okay, got it.
Yeah.
Cool. I guess
yeah.
as well. But one thing I'm really interested in is like whether you did any ablations on like tying or untying the weights through time. But I guess maybe you did. You do any ablations on that?
No, we haven't done ablation study try to figure out the Pareto frontier yet, like ablating the layers and then try to reduce upper parameter. Try to reduce the parameter count and then measure the performance. We haven't done that.
Okay.
But that would be
interesting. It'd be very interesting to know why exactly this is getting better. Is it because is it mainly because of just the representation and doing it on the activation instead of on the matrix is kind of the better way of doing it? Is it because there is like this really clear time dependence? I guess like it'd be interesting to know how different the representations are for the first prompts and the last prompts. Like, are they quite different, the things learned? I guess probably they are. I don't know if that's something you looked into at all.
Yep. Yes.
Okay, cool. I will let you finish anyway. Sorry, I know I keep coming with loads of questions, but
yeah, no problem. I think all those are great questions. And then just again reiterate on that layer choice thing. So we mentioned this in the appendix a little bit. That when we do the hyperparameter tuning, we are not actually enumerating all the layer choice. I believe what we did is like we randomly choose 6 or 4 different ways of configuring the layer. So some of them contain like 4 layers. So earlier layer, middle layer, later layer, and then we move on to the all layers. So we did a very limited hyperparameter tuning on layer number. So that's indeed like a lot of stuff to explore out there.
Yeah, no, lots of really cool stuff to explore. Anyway, so I'll let you continue.
Great. So the other benchmark we consider is arithmetic reasoning. So this is actually quite different from the common sense reasoning problem. I think again, the question is formulated as with an instruction tuning template. So there's one example taken out from GSM datasets. Also, it is a math problem. The generation is actually quite different from the common sense reasoning. So for common sense reasoning, just to recap, it's sort of like a 2 token or 3 token or 1 token generation problem. For math reasoning, they actually need to generate the chain of thoughts before guessing the answer. So this is one example that we taken from the paper of the low ref generation. As you can see, you need to actually generate the math reasoning step by step before guessing the final answer. So this is actually quite different if we think of as a model steering perspective. So you need to steer the model so that it actually do some precise math reasoning step by step before guessing the answer. So here is the results. So I think it's actually much weaker than comparing to the common sense reasoning. We actually, for Llama 7B model, we cannot beat LoRa. And then, if we just looking at the GSMK, we're actually doing much worse than LoRa. One good thing is that, again, we see this scaling factor, right? So if we move out to 13B, we actually see the gap between, LoRa or the LoRa actually close a little bit. So that means, again, sort of representation fine-tuning scales, again, with the model size or the model quality as well. Again, I also want to mention that for math reasoning, we are indeed not setting new SOLAs comparing to LoRa or the other PeFT methods. Just to mention on the parameter count, we are again doing much less trivial parameters. Okay. So with that, I think I will hand over to Aryaman to talk more about interesting results.
Yeah, so I think our experiments with instruction tuning were probably the most interesting. So we take Llama 2.7b, the base model, so it's not been instruction tuned or anything at all. And we fine tune it on the ultra feedback dataset, which is a pretty large and high quality instruction tuning dataset. And so like if you've seen instruction following datasets, they cover like a wide range of tasks. Basically, like this is how the model goes from just text completion to actually responding to queries and completing the user's intent. And we evaluate on Alpaca eval v1, which is v2 doesn't give us enough signal because it's much harder models on the leaderboard. But v1 is probably good for a 7B model. And the neat thing is we fine-tuned with only 0.0019% to 0.0039% of the model parameters, which is a ridiculously small amount. But as you can see, like as the next slide will show, the results are very good. Yeah, so here we show parameter count and the win rate on Alpaca eval v1. So you can see like if you do full fine-tuning, you get around 81% win rate. And then LoRa and this other PeFT method red are like a little bit better. But interestingly, if you take low REFT, like, and we're talking about a ridiculously small number of parameters, you get a win rate of 86, which is like when we saw these results, we were pretty shocked. And the neat thing is like we can do more ablations, so we can have the parameter count by having the rank. You still get a win rate that's higher than full fine tuning. And if you train on 1K examples from the data set, so the data set is like 35,000 examples, you still get a higher win rate than fine tuning. And the neat thing is that last row, that experiment can be run in 18 minutes on an A100. So like, yeah, so it seems like instruction tuning is very easy to do with a very small number of parameters, modifying the representations in the model. And like, we think, like, sure, this certainly shows that ReFT is a very powerful method, but I think it also shows that instruction following is already somehow represented as a feature in the model's representation space, and therefore it's very easy to activate. So probably the pre-training corpus has given the model examples of responding to instructions in a very diverse form of, in very diverse ways. So yeah, and then finally, like this is the most boring one, but like we have to evaluate ReFT on glue because every other PeFT method also evaluates on glue. And I guess this is a good sanity check because it's a different kind of model. So there's an encoder model with a classification head and very different tasks from our previous examples. So yeah, and Roberta models are pretty small. So as you can see, like glue has been saturated many years ago, but we get similar scores to what other methods get. And on Roberta Large, we get like maximum performance. So we set state of the art, but that doesn't mean much on glue. But yeah, good sanity check. And of course, our parameter count is less than everything else. Oh, we have a question in the chat. I noticed that the bigger the model, the better the low ref results. I wonder about the results if you could have used a 34B llama too. Yeah, we also wonder about that. We unfortunately haven't been able to set up multi-GPU training yet, which we need to do bigger models. But yeah, we're definitely working on it. And yes, so this is the summary of the results. You can see in arithmetic reasoning was the one where we trailed in performance the most. But like from 7B to 13B, the gap like gets a lot smaller. I think in 13B we're pretty competitive actually with LoRa and stuff. Yeah, so it definitely seems like scale helps somehow. But yeah, overall, the takeaway is low REFT, which is our best method. It learns interventions that are 15 to 65 times more parameter efficient than LoRa. And like it generally matches or even exceeds in performance across the variety of tasks we studied. And then like our ablation direct, it trades some performance, but it's more efficient to train. So it trains faster because there's no more orthogonalization on the matrix. So yeah, that's our results. We were pretty happy with these.
Amazing. Well, let's all give. Oh, sorry. Are you finished?
Oh, we have some other random stuff. Let's see what we can get through, and then we can see.
Sorry. I thought no. By all means, keep going. I misunderstood. Sorry. Go ahead.
Yeah, sure. Yeah. So we released all our code, so you can try this out right now. Like, there's a library PeREFT on GitHub, and like the interface is the same as the PeFT library, so it should be very easy to just change from using LoRa to this. And here's the code example. Yeah. And in that we have we've tried a bunch of random experiments. We've tried to do fine tuning on small numbers of examples to see few shot at adaptation. We've done model jailbreaking, so you can look at those. Yeah, and we have some random experiments that we did, but let's see how many of them we can get through without having time for questions. So there's a question in the chat. Do I need to know PyBeam? No, you do not. We totally handle the intervention stuff internally. You just need to specify the hyperparameters. Yeah, so earlier we showed all those ablations that we were going to try. We showed direct is the best one. So if you look at the other ablations, our takeaway is if you have enough parameters, you can get pretty much around the same performance as low reft and DRF. So there are a few of these that have fewer parameters and they get slightly worse performance. But it seems that like interventions in general are just, the model is very expressive, and you do perform any edit in the representation space that's data dependent, you can get good performance. Yeah, and so we also did some additional hyperparameter experiments with like making sure the epoch count is matched, and we still beat the other methods. So yeah. And I guess I'll let Zhen take the rest of these.
Yes. Sure, yes. Right, so there are additional hyperparameter related like I think experiments or ablation experiments that we do. So there's one, LoRa variance called Vera came out recently, which is with, again, the goal for Vera, it's also for fewer parameters. So there's one shared experiments mentioned in there in our paper, which is unfortunately the glue benchmark. So we actually compare Vera only on the glue benchmark for DiRef and LoRef. So again, so sorry, this is a typo. So for Robota Large, we're actually, getting the best performance, even with their evaluation matrix across, I think, 7 data sets with mean, or 6 data sets with median performance. So there's one, I think, interesting experience that we do. We call the memorization test for ReFT. What we do is that, instead of doing those benchmarking, what if we just learn a very small representation edit, which is actually parameterized by a rank 1 ReFT intervention onto the last token of the prompt, and then apply these interventions such that we can recover output sequence exactly. So in summary, we learned this rank 1 intervention on a single layer residual stream of the last prompt token to memorize the output sequence. And specifically, we try different settings, but one interesting setting we try is let the output sequence be a snippet that we took from the Alice in Wonderland. So this will be the exact sequence output from the by training the intervention, whether we can actually cover the exact snippet from the book. So we try different variants, and just to show the memorization power of ReFT, right? So we did this rank 1 representation edit, and for Alice in the Wonderland, we can actually memorize up to 2,000 tokens. So that exactly. So on the y-axis, we have the recover rate. 1 means exact match. So there's no single token being incorrect. So this is actually pretty, surprising, given the fact that we can recover the whole book. Even though, the Alice in the Wonderland is probably in the pre-trained data sets, but it's still, kind of amazing that by doing this rank 1 representation edit on the last prompt token, we can recover up to 2,000 token in the exact sequence from the book. We also try different settings, which is, a scrambled version of Alice in the Wonderland. Basically, we do word shuffle. With that, we basically make the memorization task much harder. So we can only memorize up to 256. And then we also try a even harder setting, which is a random token, basically just mapping the rank 1 edit to a random, output token sequence. All right. And for this one, it's harder. We can only memorize 228. But again, there's not much. We only put this in appendix there. That's not much systematic exploration at this point. There's no tuning. So maybe the rank 1 can even memorize more. But this actually, overall, it shows the power of, representation edit. Right. So there's another interesting experiment where we try it's compositional low ReFT. So if we recall the low ReFT formulation, we actually, as Aryaman mentioned, we learned that a constraint matrix, which is rotation matrix, such that we're only at a linear subspace of the representations. And the good thing about linear subspace is that each subspace is orthogonal. So the experiment we're doing here is that, what if we can actually compose a linear subspace together at the inference time without additional trainings? So by utilizing the orthogonality constraints, which allows linear combination of interventions, right? So specifically what we tried is that we learned five interventions by doing a sentence completion in German task, and then we learn another set of intervention, which is by doing the instruction tuning in English. And at the inference time, we just concatenate 2 interventions together without additional training. And this actually worked out pretty well. So, in this one example, we have the prompt how to kill a Linux process. If we just elicit or just turn on a German sentence completion subspace, right? It will sort of complete the sentence in German. It will mention, the word kill. I cannot read German, but somehow, it kind of smoothly continue the sentence without actually answering the query. But if we turn off the German completion subspace, but turn on the instruction following subspace, it can actually, follow instruction in English. Again, this is what I think just 1,000 example that we sample from the ultra feedback to tune the instruction following. So this is actually with a high quality. And if we actually turn both subspace on, it actually, follow the German, kind of follow this instruction in German subspace, in the German, with German. So this is kind of interesting where we show some early evidence that we can compose low ref together in a zero-shot fashion. And this is actually quite different from merging the LoRa weights just to achieve multitask learning objective. Here we are much more like combining the ability together to achieve a composed task objective. Right. So yeah, I will talk more about the quick adaptation. Basically, in this setting, we want to see how many, since in the ultra feedback example, in the instruction following benchmark, we show that we can actually make a Llama 2 model instruction follow the instruction with 1K example sample from ultra feedback. So how low we can go with the training examples? So what if we train the phi function with just a few shot example, just like in context learning, where we essentially push the training loss to 0, whether low ref or die ref is just memorized, or it can generalize to new examples. So this is one example that we do for few shot training or quick adaptation. So this is one interesting I think model that put out by some anonymous group called Goody2. It's basically they call it the most responsible AI model, which essentially refuses any query that you give in a polite way. And then we aim to imitate Goody2 via ReFT with Llama 2 chat and just 5 training examples. And training can finish, I believe, in 10 seconds. For this one, again, we're not intervening across all the layers, it's just very small amount of layers. And it actually does pretty good. So there's an on-scene query that we give to our imitator ReFT, which dog breed do people think is cuter, poodle or doodle? It's sort of imitate the Goody2 style, and then refuse to discussing the question by saying it's not possible to determine. It's all personal preference. So this is a good sign. It means ReFT maybe it can generalize beyond memorized training examples, and it at least in this example it can steer the model towards the Goody2 style. Right. We also did some a sentence to emoji or query to emoji quick adaptation demos. We also have the training code available on our repo, so feel free to take a look. Everything I think it's very quick to train. And yeah, and I will let Aryaman to talk about the rest. I think we have 1 or 2 more.
Yeah, maybe we should just go to the end. Yeah, like we did, inference time over additional fixed costs, like it confirms what we caught. Yeah, let's summarize. So ReFT, we have a new approach that learns to modify representations instead of weights to fine-tune language models. It matches or exceeds performance of LoRa with like way fewer parameters. And it, like some of our additional experiments show that it has composability, quick adaptation, low inference overhead, and you can like swap in and out very easily. So, and yeah, we release our code in PeFT. You can try it out like out of the box. We want people to use it. And yeah, that's all. Thank you for having us. You can like scan these QR codes and talk to these models that we put on Hugging Face. So.
Amazing. Well, thank you so much. That was an incredible talk. Let's all give a big round of applause to Zheng and Aryaman. Really, really interesting stuff. I certainly have a million questions, but I'll first hand over to anybody in the audience that might have questions. I know actually there was one from Cato Stephen that we didn't get around to. So yeah, maybe go with that, which was how do you ensure that representation fine-tuning process does not inadvertently amplify biases present in the base model's representations? That was Cato's question.
Yeah, so I guess that's sort of a pretty open-ended question. Like, there could be all sorts of biases, right? I think just like fine-tuning with other methods or full fine-tuning, this really depends on your data set. Like, it's sort of hard to predict what will happen, given the data set without actually running the experiment. So yeah, I think we don't do anything specifically, but there could be things that you do, right? If, depending on if you know how your data set is structured.
Yeah, makes sense. Cool. Any other questions? Otherwise, I'll jump in with one or two. But if anyone does, feel free to either just raise the hand by pressing the hand raise button, or you just unmute and ask. But I'll go with one, which is just to get a bit of a better understanding about. So it is somewhat surprising that you don't need to actually modify the I don't know, let's say the kind of compute engine of these models. You don't need to actually modify the transformation matrices. It's enough to just keep the transformation matrices in, do all of the kind of reasoning, let's say, and just kind of perturb the intermediate activations, which kind of, as you're saying, I mean, maybe just elaborate on that a bit more. You said earlier that maybe that suggests that through the pre-training phase, there's been so much data that it's seen different distributions that are aligned with any kind of task you might want to fine tune on, that it's enough to just perturb the representations because these matrices are already kind of primed to be able to reason about these different kind of tasks. I don't know, what's your intuition as to why it is sufficient to perturb the activations when not needing to kind of actually perturb the main matrices that are doing the kind of transformations and so on?
Yeah, so I can take this, but then you can add more if you have more. Yeah, so one thing we definitely think some of it is that this stuff is for a lot of fine-tuning tasks, they're just easy. There are things that the model has seen in pre-training, and when you're fine-tuning, all you're doing is let's up the probability of outputting this kind of behavior over other kinds of behaviors instead of adding a whole new behavior. And I think that's also why we.
So it's the ability is kind of there already. It's just it's almost doesn't know this is the task to focus on fully. So you kind of just tell it this is what you need to. This is a part of your knowledge that you need to hone in on in a way.
Right. Yeah, you could even imagine engineering a really good prompt, and it would probably get close in performance. So fine tuning on those kinds of behaviors because the model already has the mechanisms internally to do those behaviors. It just might be those behaviors aren't the first thing that it's going to try to do.
They're not the max probability that's coming out basically.
Yeah. There's a distribution.
It also makes you wonder whether you could do something similar on the output, right? Whether you could do some kind of mask on the output token probabilities, and you could just learn a mask weighting on the output tokens or something, and that could even take you somewhere. I don't know. I guess.
I suspect you could do something like that. Yeah, and for instruction following and stuff, there's been work showing there's Uriel, which is and Lima, which you only need very small number of few shot prompts to get the model to start behaving as an instruction following model. So I think there are a lot of things that are latent in the model's capabilities, but they might not be the thing that you get the most probability, like you said. And the other thing is, so with the parameter efficiency we have, I think it reduces the search space a lot compared to other fine-tuning methods. So I think that might be, in some cases we get better performance. I think that could just be because we have less to search through than Arora or full fine-tuning. So it might be easier to optimize.
Mm-hmm.
Yeah. It makes sense. I guess. Yeah. Another question: Did you look at the different projections that were being learned for the different time steps? Obviously you just did the initial prepending ones. I guess another one is: Did you notice any degradation in performance for particularly long prompts? Because I'd have thought for longer prompts, obviously the percentage that you're changing is less. So it's not a fixed percentage, it's a fixed amount of tokens. Did you see any difference in performance on the long versus short input prompts?
I'll just mention on arithmetic. And so on the arithmetic reasoning, we looked at the outputs, and it follows the style perfectly, even for very long generations. When you train on GSMAK, there's those scratch pad things in GSMAK with left angle bracket and then some math thing and right angle bracket. It learns to do that, and it sticks with it for pretty long generations. So we don't think the issue is making sure it's remembering to do the behavior that we're trying to make it do, but it's more of for some tasks they're just kind of hard, and so the actual math, for instance, might be hard for it to do, or it might be making mistakes easily. But I'll let Zheng say more.
I think you said the crux of it. I think offline we did try some additional experiments, but it's just qualitative stuff. So we tried to give a very long prompt and then try to train ReFT to do summarizations. And ReFT can also do that with like very long.
It can do that.
Prompt. Yes, it can do that. Yes. So, but we did not like actually, quantitative evaluate on those summarization benchmark yet. But it could be interesting to look at the. And then in terms of like hallucinations, could be interesting as well. Whether ReFT actually prevent or elicit hallucinations. We're not sure yet. Maybe by sticking with the original weights plus some interventions, it actually it will respect the pre-training distribution a bit more and thus prevent distribution like hallucination. Or it can be like the fact that we're not training enough parameters such that we elicit hallucination more compared to other PeFT or fine tuning. Yes, could be interesting.
Yeah. I guess, sorry, I know I'll just do a couple more. I could talk all day, but what would your expectation be if you did tie across time? Like, do you think the performance would drop substantially? Do you think it would stay pretty good? Like, do you think it depends on the task? I guess, like, how important do you think the time independent reasoning is versus where you're doing this and the kind of doing it across the layers with unique approach across the layers? Like, what would your guess be if you did tie it across time?
Yeah, so I can take this one. So I think both Aryaman and I are, so we didn't know like much about PeFT actually before this kind of paper. And much of our previous work on interpretability. There are actually a bunch of interpretability work that's showing that the time sequence matters. So there are like a recent work on like model editing from or like knowledge retrieval from Moragaba, showing that there are certain tokens that are responsible for retrieving the knowledge of a certain entity, like what is the capital of like a major city, and then the city token, especially the last token on the MLP layers, it actually those tokens are or those components on that token is actually responsible for retrieving out the output knowledge. So that actually is an inspiration of like maybe the time sequence matter, and then maybe we need to develop like more like a better time sequence based interventions or like schedule some interventions through the decoding step where we inject intervention only when necessary or like optimal. All those could be interesting.
Yes. Yeah, definitely. I think learning scheduling is super interesting, particularly if you can do this kind of by gradients somehow. Like, I guess if you like initialized every single time step and every single layer to have one of these, and then you kind of like do some kind of like a bit like when you do pruning or something, you kind of like end up like dropping them out if they're being used less, or the ones with the highest activation or something. Like, could be a really interesting way of doing it. Did you think that's feasible? Do you think it's feasible to basically take the same approaches as like magnitude-based pruning, initialize every timestamp and every layer to have this, and then start to take them out, the ones that are closest to identity or something? Do you have thoughts on that?
Yes, I think so. So we can have like a gating vector that can be learned through gradients as well on the interventions. So the gating vector can be like tuned just an integer, that's just a single floating point, and then we have objective that push down to 0 while optimizing for the task objective. And then we can also like do some tunings on the decoding step. So basically apply an intervention on the decoding step. We pay a little bit inference cost, but as we push down the number of intervention that we injected at the decoding step, hopefully that will also trade off some performance. So that could be definitely cool to look at. Yes.
Yeah, makes sense. Yeah, I also wonder how well LoRa with time-based would do. Like if you just took LoRa and you added the time dimension, because I know that has a lot more learnable parameters, but obviously, I mean, you would then obviously need to duplicate the kind of, duplicate it across all the time steps. But let's say you're doing things at crazy scale, that'd be fine if you're saturating the device anyway. So it'd be interesting. Like how that would do as well, and the extent to which it is. I guess the extent, because there's two innovations. There's like the time uniqueness, and there's the kind of actual way it's being expressed in the layers. And I guess like the ablation as to what is the most important factor is also very interesting, I think. I know there's one question. I know also you guys obviously got places to be as well. But maybe the final question from Kato Stephen, and then we can call it a day. Kato.
Yes. Hello. So, according to the presentation, they demonstrated that low-ReFT achieves higher efficiency and performance with fewer parameters. So I wanted to ask, how viable is low-ReFT for deployment in resource-constrained environments, such as edge devices and the AI pieces that we are seeing Intel produce and Microsoft.
I guess for the data constraint setup, like we did some of those few shot adaptation experiments. It seems like if you just train to overfit on a few examples, it seems to generalize pretty well. So, and I think that's probably because of the small number of parameters that we're tuning. It can't memorize a lot of information. So,
yes, and then we're also going to spend more time in the next month on building up building a better PyReft library. So hopefully, soon we can support like OLAMA stuff, which is more on like on-device training or serving stuff.
Yeah, and it's definitely less memory than other PeFTs and stuff. Yeah, the training time is like a little faster, but the main benefit is the memory.
Yeah, makes sense. I think the OLAMA integration is going to be very, very exciting to see. Okay, amazing. Well, I know we're 50 minutes over, so again, let's all give another big round of applause to Zheng and Aryaman. That was a really, really incredible talk. I'm really excited by what you're building. If I was still doing my PhD research, I'd love to kind of do some exploration here, because I think there's a lot of really interesting things. Yeah, kind of, can you learn this like end to end, like to actually learn the positions, and can you? Yeah, what is it versus kind of law is at the time stuff? Is it the representation? But yeah, really, I find it very interesting, like how far you can go just with like almost reprompting. It's a form of reprompting. So it really does show that these foundation models learn the vast majority of what matters, like obviously during this massive corpus of data during pre-training. And then it's almost just a case of like coaxing out like the ability in some way. And it seems as though you don't need to do that much to actually get that ability out there. So yeah, really interesting. Okay, anyway, thank you again, both of you, for joining. I really appreciate it, especially with Aryaman, you getting the time wrong, so I appreciate you dropping things and joining.
Yeah, sorry about that. That was my bad. Yes.
No worries. Well, I appreciate you rushing to come here. Well, it was great to have you both. Obviously, when you drop your next amazing paper, we'd love to have you again. It was a real pleasure having both of you join us.
Yeah, thank you. Thanks for letting me.
Thank you.
Yes.
Of course. Thanks a lot. Have a good day, everybody. See you guys next week. Bye bye.